mic won't be able to catch that. Home percentage. I don't know how it turns for the online participants.
Anyway, so last year I gave a point on almost the same topic as almost the same title, but it was all kind of statements and then implications and so on. So this time, since it's in-person board talk and since this is a specialist audience, I thought I'll give some details. Okay, so it's going to be technical talk with a sketch of the proof. Okay, so let's see how it goes. So feel free to ask questions. Anyway, so let me recall the statements. So this is recall from last year. So F is a totally real number field. And H over F is a finite abelian CM extension with Galvin group G. So G is the Galvin group of the H over F, which is a finite abelian group. I need to define some L functions. So let me with various decorations. So let me introduce that. So S is the finite set of places of F containing all the places that ramify in H and all the infinities. And D is another finite set. Finite non-empty. Places of F, which does not intersect with S. Okay, so I'll define this decorated L function for any character I of I. So this is product over all places in P, 1 minus chi of Q, norm of Q to the, sorry, sometimes my Q is like this. 1 minus S, LS, chi of S. Okay. And what is LS chi of S? This is just the L function with all the factors that S removes. So chi of S, this is product over all V which are not in S, 1 minus norm of V to the minus S inverse, and of course all this makes sense a priori only for real part of S bigger than 1. Then you have a meromorphic continuation to the whole complex plane. Possibly a simple pole at S equal to 1. So all the usual things which I'm not going to say much about. Okay, and chi here is of course the character of G, and I take its values in Q bar because sometimes I want to look at it as a p-adic character, sometimes I want to look at it as a complex character. So I should, to begin with, I should fix an isomorphism between complex numbers and CP. Okay, but anyway, I'm not going to write all these things down. So here's the object, the first object that goes into my statement. So theta is Th over F. This is the so-called Stickelberger event. Okay, so now this is a unique element in the group ring over complex numbers, which satisfies the following property. Chi. So remember, chi would give you a map from CG to C. You extend it linearly. So H over F. This interpolates these L values. So L, S, T, pi inverse Z. Yeah, this is a primarily complex number. So there exists a unique element in the group rate which satisfies this. You just take these values multiplied by the idempotent pi inverse and take the sum over all chi. Right? It's that's what we learned in the first representation theory course on finite groups. This is just a billion anyway. So here's a very celebrated and important theorem of Ziegler-Shintani, Casanova. And then we limit, which says that this element which a priori is in, yeah, okay, so maybe I should put one more condition on T. T contains two primes of different residue characteristics, of distinct residue characteristic. Okay. So two primes which lie above different primes in. Right. So this thing is an element of Z. Okay. So without this condition P or without this P smoothing, you would only get an element in QG. That's the result of Ziegler and Shintani. But with this modification at P, multiplying by these finitely many factors, you actually get rid of all the denominators. So that's the result of Casanova's theory. Okay. So that was one side that I spoke about last year, and the other side is the class group. Okay, so this talk is about class group and a little bit about many related topics. So L functions, modular forms, Galois representation. All right. So the class group I want is again with some kind of modification at both primes in S and primes in. So what is this? This is the class group with modification at P modeled by classes generated by primes of S. Okay, so you're killing everything in the class for the classes that are generated by primes of H above S. And what is PLT? PLT H. This is non-zero, but these are all fractional ideals. Prime to P, which means that fractional ideals which are prime to ideals above P in H, modulo principal ideals, principal fractional ideals generated by alpha congruent to 1 modulo T, and I'll again write it like this, which simply means that it's congruent to 1 modulo every prime in T. So if you would like to think in terms of Galois extension, then this is the maximal abelian extension of H, in which all primes above S split completely, and all primes in E are at most stably ramified. And everything else is unramified. All right, so here's the conjecture of Rumor star. Sometimes I also put name of state in it. I put together the two statements that Rumor and star made independently. But this form of the statement that I'm going to write down is due to Rumor. So it says that theta st H over L. This is an element in Z, right, because of this theory. this actually belongs to the annihilator ideal of this class. Okay, so you take all the elements in ZG that annihilate this class. So because we know that the class, this class group is a G module, right? G acts on all of fractional ideals trying to T, and it takes principal ideals to principal ideals and so on. So we get action of ZG on this class group, and you take the annihilator. The lecture says that the Stickelberger element lives in this. So remark, this generalizes Stickelberger scale, classical 19th century Stickelberger's theorem. This is from 1890s, please. For the case F C equals to Q. Okay, so in the case F equals to Q, the statement is precisely Stickelberger's theorem. I mean, even though it's probably not stated this. Okay. All right. So what can we do? This is the theorem that we are going to see a sketch of. Yeah. Proof. I'll sketch the proof of this. What I wrote here. Forgot what was doing, I guess. Okay. So yeah, okay. What we prove is we prove this theorem away from P equal to 2. Okay, so this belongs to the annihilator ideal of H tensor with Z1 over 2. So there are, I mean, as number theorists, we know that P is equal to 2 is always a difficult prime, or at least in most cases a difficult prime. And here it's the same. P equal to 2 is hard. There are conceptual difficulties in making our methods work at P equal to 2, but there's some hope. So this is work in progress, and hopefully it will be finished soon. So I hope that within 6 months we can remove this tensor. During the sketch, I'll tell you what the difficulties are, but not say anything about what the solution is. All right. So that's the statement. And so this side is a completely arithmetic algebraic side. This is the analytic side. Okay. Now, the methods that we use are the methods that are kind of known for relating arithmetic side to analytic side, coming from Iwasawa theory or special value or conjectures on special values of L function. The most general method actually tells you how to prove that something arithmetic is contained in something generated by analytic objects. So it tells you how to prove the reverse inclusion. Okay. Now that's no good unless this is an equality. I mean, if you know that the ideal generated by theta is equal to this annihilator ideal, then one can at least, well, not know, but if you expect that the ideal generated by theta is equal to the annihilator ideal, then one can at least try to prove the reverse inequality. But in general, it is false that the ideal generated by theta is equal to the annihilator ideal. Okay, so that happens very rarely. For example, if this is a unit and this is zero, then it would of course happen. But in general, it doesn't. So here's a refinement. But before that, let me give some notation. So M is any ZG module. F check is contragant dual of M. M minus this is m tensor by 2, and then I take the C is the complex conjugate. Complex conjugation. Remember, we have a CM extension, right? So there's a unique complex conjugate in G. And then I also have fitting ideals. I'm not going to define what a fitting ideal is. But let me give you the statement of the refinement. This is usually called the strong Rumer-Stark conjecture. Okay. It's called strong Rumer-Stark. This is due to Greitzer and Kurihara. Okay, the statement is due to and again we prove this thing. So this says that maybe one more notation. So is an involution of ZG, which just takes it's a Z linear map generated by G going to G inverse. So to make everything. So theta SE H over M. This thing is contained in the zero is fitting ideal. ZG minus, or you take the ST class group, okay, take its contract into a line, and actually also take its minus part. Okay. So this is contained in this idea. So that's so this is theorem 1. So this is theorem 2. See? And so here's a very rough sketch of how theorem 2 implies theorem 1. So, so from this, I want to deduce something about annihilator. So here are three facts. So first is fitting ideal. So these are all well-known facts about ideals and annihilator ideals and so on. This is contained. So fitting ideal is always contained in annihilator. Okay. So this is always true generally. So I can do this. Second is so fitting ideal is the refined invariant, and so we have found something analytic which lives in something smaller. Now there is all this minus and check there. So for a finite module, maybe I'll put minuses here. CLESH check. This thing is equal to the annihilator ideal of the class group, but with a hash applied. Right? So if you take contrary to, you just change the ideal by applying hash to. So it's kind of easy to show as well. All these are very easy things. And the last thing is theta SE lives on the minus side. Okay, minus side. What this means is that I theta S H over F is equal to, it's this L value, right? And we know that this L value is 0 if chi is not totally odd. It's not a totally odd character. So from the minus, so there's nothing to prove on the plus part. We know that the L value itself is 0, and so 0 annihilates that. By the way, already in this statement, I'm inverting 2, so I've already gotten rid of the prime now. But that's not part of the problem of dealing with two, because there's a problem in the proof of that I'm going to sketch this. Okay, so at least we have a refined invariant now. And again, as I said, the method that we use, the general method in Iwasawa theory is to show that something algebraic is contained in something analytic. So maybe at this point you would hope this ideal, the ideal generated by theta in ZG minus is equal to the fitting ideal. One could hope for that, but unfortunately that's also rarely true. Okay, so it's not truly general that the ideal generated by theta is equal to the fitting. So again, it's kind of a non-starter for our proof. So we need a further refinement. Okay. And I'm going to be very brief about that. So what? Yeah, the lucky thing for us is Burns, Kurihara, and Sano had exactly the right statement, where they described what this ideal is in terms of fitting ideal of some arithmetic object. There are various questions you can ask at this point. You can say, okay, this ideal is, yeah, because I wrote it like this, let me say. So if this ideal is not equal to this, what exactly is this ideal? Can you give an analytic description of this? And there is an analytic description of this. We prove, so it was conjectured by Kurihara, and we proved that conjecture. Or you can ask, is this ideal fitting ideal of some natural arithmetic object? And again, that's the conjecture that Burns, Kurihara, and Sano made. And as I said, this was very fortunate for us. So that's what I'm going to tell you next about. So Burns, Kurihara, Sano, and before that, Ritter and Weiss. So actually, the construction that we use is due to Ritter and Weiss, and this is much older, from late 1990s. This is, I think, from 2014. So they define an object that I'm going to call nabla TSH over F that sits in a sequence. Okay. Such that there's some short exact sequence that I'm going to write down here. CLTSH minus nabla STHL. So it's an extension of something here by the class group. And what is that something? So this is H S minus S infinity. So S infinity minus what is YH to Y S minus S infinity. This is pre-abelian group generated by the places of H above S minus S. Okay, so this is some very explicitly abelian group. You kind of would think that one understands this well. And then this nabla is a certain extension of. So this is also like the unit group for units in H, right? And by Dirichlet's unit theorem. So these are units, and then there is class group, and then this is certain extension that comes from class field theory. Okay, so some very explicit object that is given by the fundamental class of class field theory. That sits here. Sorry, I'm putting minuses there. Okay, and then the next that we prove is the following. So in fact, fitting ideal in ZG minus of this nabla minus this is exactly equal to the ideal generated by theta. Okay, this time there's no hash there, and that's not a typo. There is no hash there. Okay. So how do you deduce theorem 2 from theorem 3? So you have to prove something else about nabla that I haven't told you. You have to prove that it's what is called quadratically presented. So if you take quadratic dual of this, then the fitting ideal of that will generated by theta hash. The quadratic dual of this will subject to the quadratic dual of this. And whenever that happens, the fitting ideal of the quadratic dual of this will be contained in the fitting ideal of this. Okay. So fitting ideal over ZG minus of this quadratic dual is contained in the fitting ideal ZG minus of CLTS. So you will know that theta belongs to this, and so it is contained in this as well. So that's how theorem B implies theorem 2, and then theorem 2 implies theorem 1 as well. So okay, so now we are in good shape. Okay, we are going to prove the reverse inequality that what the kind of reverse inequality that the kind of inequality that appears in Hoover star. Okay, so step 0 is will show enough to that this fitting ideal is contained in this fitting ideal of ZG minus nabla ES H over F minus is contained in the ideal generated by. So let me reiterate that this is the reverse inequality than the kind of inequality that Blumer's law has. So it's very important for us to have a vector which gives which is equality. And then you have to do it for all extension H over F. You need to have this inequality for all extension H over F to deduce an equality. You can't do it just for one extension and then deduce equality. So this is some application of class number formula. Because when you specialize these two with respect to each character of G, this side gives you L values, this side gives you orders of some class groups. By class number formula, you know that they are equal, and then somehow you patch them all together and show that the equality also holds in the group ring itself rather than just two numbers. So it's some kind of delicate matching together, but maybe not so surprising if you're doing it yourself. All right, so that's step 0. Now step 1 is we'll reduce it to construction of some Galois homology class. Okay. Again, this is the kind of thing that is standard in universal theory. So so what we'll do is we construct module ZG minus module B and a suggestion from B to now. So what does let me finish this sentence. So what does this mean? This means that this means that nabla is big. I mean, it's at least kind of as morally speaking, it's roughly as big as that mod ZG theta. So you have to show that this is big. Okay, it has lots of elements. And that's what we know by work of Rivet, Wiles, Weiser-Wiles, how to construct elements in some arithmetic objects. Okay, so that's what we are going to do. We are going to construct some object with a surjection on this, and then we'll show that this object is large. with the circulation and so module B with the circulation and fitting ideal of B is contained in theta. So this shows that B is large enough, okay, and so theta will be lambda will be large. Okay, and for this, what is so as I said, this extension comes from class field theory. So you can imagine that to get a surjection from some ZG module to this, it's enough to construct elements in some homology. So for this, it's enough to construct some kappa in H1 GFB. So B is then ZG module, right? And there's a surjection from GF to G. So it becomes a GF module. So that's what I mean when I write like this. Such that it satisfies a bunch of properties. Okay. So one is kappa is unramified outside T, okay, locally trivial and S, and stably ramified and stably ramified at P. And these shouldn't be surprising because that's exactly what I said about this class group. Okay, this corresponds to Galois extension, maximal abelian extensions of H, which is unramified outside T, completely split at S, and at most stably ramified at T. So we need similar properties from our homology class. And now you can take kappa. So you have a restriction map from F to, so this is the restriction map from F to H. But now this is the ZG module, right? So GH acts trivially on B. So this is actually home from GH to kappa to B. Okay, and so kappa here goes to let's say kappa bar, and B0 is image of kappa bar, let's say. Okay, so then what I want is I want a surjection of B0 to this YH. Right? So there's some part which takes care of the classical part, there's some part which takes care of the one part. And then there's some compatibility with respect to the extension. So this I'm not going to write down. So some compatibility. In this X group. Z G minus, so let me write here X1 Z G minus Y S minus S infinity minus then B. There should be B. Sorry, B0. Okay. So this third point I'm not going to write this, but it's, you can imagine that nabla is some kind of extension, and you need certain element in this X group, which will give you surjection to nabla. Okay. All right. So how do we get? So the problem is finally reduced to constructing some homology class over some global Galois homology class. Okay, and Since referred to converse to Herbert theorem, that gives a very nice way of constructing global gamma cohomology classes. But then the problem is how do you show all these local properties? Yes, so each of these steps one has to do. One has to construct a global Galois cohomology class, and one has to show all these compatibilities and local properties. Okay, so let me tell you how to just go here. So that was step one, reducing into construction of Galois cohomology class. Now, step two is constructing some cusp form. Okay, so constructing a cusp form. And for this, what I'm going to use is some yeah, so the notation will put okay, so what I'm going to do next is I'm going to now I'm going to work prime by prime. And I put some simplifying assumptions for simplicity. Assume X over F is the unramified. This is unramified. And we also fix an odd prime. So in fact, this is the hardest case in some sense. H over F unramified. Ramification away from P is hard. Sorry, unramified and P is the hard case if you work on this kind of conjecture, then P splitting completely in H, that's the hardest case. So here we are doing it as computational simplicity, but this captures the sense of the methods anyway. And then I'm going to work prime by prime, and again I have to stay away from P equal to 2, of course. Okay, so these are kind of modular forms of weight K, but now with coefficients in Z. Okay. Yeah, modular forms. With ZVG coefficient. What this means is, I mean, if you want to think very naively, you can think of these just as Q expansions. Okay, so you can think of collection of Q expansions with coefficient in ZPG minus, so that when you apply character of G, you get an actual modular form with coefficients in some finite extension of it. Yes, you get an actual PID modular form. So this is just like Hida family, but now the extension is not a cyclotonic ZP extension, it's a finite extension. It's a finite. So you can think of these like Hida families, you have seen them. Okay. So what's a good thing about this is you can actually so now theta ST H over F, I denote this simply by theta. Okay, so this notation from now on, I'll just denote it by theta. So there exists an Eisenstein series WK in I'm not specifying what the level is and so on. Just I don't really need to specify the way I'm presenting it, but so there's an Eisenstein series with constant curve. SP H over F, but now with value at 1 minus K. Okay, so yeah, it means if K is equal to 1, you get your original impact. That's it's evaluating interpolating values of the L function at s equals 0. This interpolates values of L function um, at s equal to 1 minus k. So there is some Eisenstein series WK. Now, so usually these are denoted k, but this is a modification of EK, and the reason we call it WK is because when we wrote it down, we thought this will never work. It's kind of a very wacky construction, completely mad, so it's not going to work. So, but it worked, and so we decided to call it W. So what is so in terms of this W, you can write down a modular form. So I'll write it down and then I'll tell you what is this. So there's W1, weight 1 modular form. So that is the one which will have your theta dash as the coefficient. But I'm going to subtract, let me write an X here, but I'm going to subtract WK. And this makes no sense because the weights are different. So you have to multiply it by some weight K minus 1 star. Okay. And then X theta dash. And then there's some HK here. So there are lots of things I need to explain. So E is Hita's idempotent. Hita's ordinary projection. This Vk minus 1 is lift of Hussein invariant. So this is a weight K minus 1 stuff. Level 1 modular form, which is highly congruent to 1 which is congruent to 1 modulo high power of P. Okay, so V K minus 1 is congruent to 1 modulo P, some large power, depending on K. This HK is some specific. This is some construction due to Silliman. This is due to Silliman. So this is some. He shows existence. Silliman shows existence of something. I'm not going to tell you what properties I need. But it's the thing which will make it hospital. So this thing is kind of Eisenstein. This thing has some Eisenstein component, and then when you subtract this, it becomes hospital. And X is some weird stuff, which is theta ST. Sorry, I'm just going to stop writing X over F now. And again, this is highly congruent to 1 modulo P to the large power. Okay. So there are all these objects in here, but the main point is, after doing all this complicated construction, so you have to really understand the constant terms of all these Eisenstein series at each class, and then you take this linear combination and you explicitly kind of show that it has no the constant term at each cusp of the Hilbert modular variety is 0. So that's how you show that it's a cusp form. You actually show it by hand. So there's no other way I know. Constructing a cusp form, you write something down explicitly and then you show that it's a cusp. But the nice thing about this cusp form is modulo some large power of P and X theta. So X theta dash. It actually looks like Eisenstein. So it looks like Eisenstein. Looks Eisenstein. And this is always the case. You construct something that's which modulo some idea looks Eisenstein. And so which means that when you take Galois representation attached to this cusp form, modulo that idea of the Galois representation is actually reducible. Okay. And so you can construct homology classes. So that's the philosophy behind it. Now T is some Hecke algebra, Hecke algebra. Again, I'm not going to specify. Sorry, I did not say what. So this lives in SK, ZP, G minus. Okay, that's SK. Hecke algebra, hospital Hecke algebra. So hospital Hecke algebra generated by ELs and then the diamond operators. Diamond operators. And ZELs away from primes above P. So this custom gives us two things. It gives us homomorphism from the Secchi algebra into some nice ring that we are going to use. And then the second thing it gives us a Galois representation. Okay, so let me write down these two things. So one, there exists a homomorphism from this. Yeah, and so this is T and then T tilde is in the T, and then you also throw in the UP operators. But Hecke operators. So, yeah, so there exists a separation from this onto some W. I'm not going to write down what W is explicitly because I don't need to. Such that well, the first two conditions are that it looks Eisenstein. Okay, so phi of diamond operator is just the class of this G. This is what an Eisenstein. This is what diamond operators would do on Eisenstein series. Similarly, for DL, you would get the cyclotomic, the p-adic cyclotomic character evaluated at L plus the canonical character. So this is also in ZG. And this is exactly what TLs do on Eisenstein series, right? So this W is ZG minus X theta hash algebra. Okay, but now of course this means nothing. I mean, this is all in W. So this is also in W, but there's a copy of this inside W by the structure. So this all means nothing because W could be 0. So I need to say something about W being large enough, and that's what this last condition does. This is an important condition. Unfortunately, I won't have time to tell you why this is used, but this is the most important thing. Okay, so if you take this particular Hecke operator and hit it, and apply it for Y for some Y inside ZPG modulo X theta. Then this Y is actually, okay, sorry, let me write it. It's inside ZPG. This is a ZP here. Algebra. So then this Y actually lives inside the ideal level. So this Y is not some arbitrary thing, you know, it lives inside this country. It can't be too small. So this is the most important condition. As I said, unfortunately, I don't think I'll have time to say anything about it. So that's yeah. The last thing I want to see in a couple of minutes is now getting a representation. So there exists a representation between GL2 K. So K is fraction field of total ring of fraction of K delta. Such that, so this is being be done twice, that there exists such a thing. So if that rho is unramified outside the P, but the most important condition is that when you restrict rho to decomposition groups, it becomes the upper triangle. It becomes kind of upper triangle, and you can say precisely what these two things are. And you choose. So what you do is you. So this is, yeah, and then of course, yeah, okay. Let me move on. So choose a basis of this representation. Choose a basis for rho carefully, whatever that means. You have to be do it carefully. So, and then you can write it as this. And because you have kind of been careful in choosing the basis, what you can show is that your A and B have very specific form modulo your ideal. Modulo you can, and so once I do that, I can tell you what B is. So I be the kernel of phi. So what you can show is that A sigma is congruent to the p-adic cyclotomic character to the -1 modulo I, and B sigma is congruent to a class of sigma. This is again in W, but this is also modulo I. Okay, and you can then just take B tilde to be the key module generated by B sigmas. And B tilde modulo I and C tilde. So if you just write down what it means, what this means for B, then you can show that your kernel of sigma, this is sigma inverse B sigma. This actually turns out to be an element in H1 here. B tilde modulo I. So it actually turns out to be an element here, and this is then you show the element that you wanted. This is the module that you wanted to construct, and this is the homology class you wanted to construct. So now you have a look at it. Once you have that, you can try to show all these properties that that I had mentioned for the module that we have seen. And so this theorem goes into proving that. Let me just say what goes wrong at p equal to 2. At p equal to 2, we can't show this for some reason, and so we don't even have a homology class using this method that I'm telling. Okay, so that's.
Thank you, Mahesh. I think since we're a bit over time, we'll defer questions until and we'll go on to our second speaker. Are you using the board?
Yes.
Okay. Should do that.
Yeah, so we can have the questions. Sorry, I think we'll let you do it.
Yeah.
I'm sure there'll be quite a few people who will be interested.